welcome to my talk. I'm Valentin from ThinkCell Software. You may have noticed our lounge outside. So thanks for joining in. And just a disclaimer before I start the talk. So I'm not going to teach any best practices for concurrent programming or advertise any particular programming style. And this talk will also not be about how to squeeze the maximum performance out of a certain multiprocessor system. So instead, we will focus on the foundations of concurrency in C++, which is the memory model. So why do we need a memory model? So usually we have source code, and yeah, we can look at the source code and see what it does, right? But as a matter of fact, your machine does not execute your source code directly. So what happens? Say you have some piece of code like here on the left, and you know there's statements. These statements describe operations on variables, which are somehow operations on memory locations, as you all know. And yeah, but before you can run this code, you obviously have to pass it to some compiler, which turns it into machine code. And this compiler may elide some of these memory operations. It may even restructure your entire program flow. And then this code is going to be executed by a CPU, which may perform speculative reads or writes and execute stuff out of order. And in the end, finally, because memory is low, we have several layers of caches. So these are all optimizations that we need to get the speed we want. But the question is, do we need to be concerned about this? Well, usually we don't, because we cannot observe these optimizations directly. So usually the outcome of the program would be the same as if we had this simple machine which just would execute one statement after the other in the order specified by the program and operate directly on memory. But what happens now if we say we have two threads of execution? So and at some point eventually we want to synchronize program flow between both threads. So a newbie programmer may read Wikipedia, for example, and somehow discover Dekker's algorithm for mutually exclusive execution of a critical section. And for those who are not familiar with this algorithm, it basically works like this. So we have two threads, and every thread has a dedicated Boolean flag. And whenever someone wants to enter the critical section, he first has to set this flag to signal to the other threads, hey, I'm going to enter this critical section now, everybody step back. And then you check if someone else has already set this flag before. And if nobody did, well, you know you're safe to enter the critical section, right? So great. Yeah, but of course, you all know this code like this will not work on a real computer. And this is because all the optimizations on memory operations that are done in one thread suddenly have affect the behavior of the execution in the other thread. So this as-if rule doesn't hold anymore if we have two threads of execution. So yeah, so it feels a bit strange if when we write a program and we want to write portable programs that suddenly our program correctness somehow depends on architecture-specific peculiarities. And therefore, of course, you shouldn't write your mutexes yourself. The C++ standard library already brings you mutexes that work out of the box. But even if you have them, you still need some kind of model when you operate on shared memory that tells you if your operations on these shared variables are well-defined or not. And on the other hand, this memory model, which the C++ standard defines, also is kind of a blank check for compiler optimizations. So it tells the compiler what kind of optimizations are allowed and what not. So in this talk, basically, first I want to give you some fundamental key concepts, which in my opinion, every programmer should acquaint himself with, at least when he writes concurrent programs. And when we are done with that, we will we'll focus on the maybe most discussed feature of C++11 concurrency, which is explicit memory ordering for atomic operations. So first we need two definitions. So first we need to define what a data race is in terms of the C++ standard. So I just copy-pasted the essential text from the standard here on the slide, and it reads, a memory location is an object of scalar type or a maximal sequence of adjacent bit fields. So this basically means whenever you have some variable of built-in type, like an int or a char or a pointer, then this will be separate memory locations. Only in this example, when you have these bit fields, A and B, they alias into a single memory location. So keep it in mind if you use these bit fields. So, and when we have two or more operations on memory, have two or more actions on memory, and that both operations access the same memory location and at least one of them is a write. That's called a conflicting action. So for example, if we have two threads running in parallel and one thread writes to A and the second one writes to C, that's not a conflicting action because they are two different memory locations. What if both threads simultaneously read the value of the pointer? Is this a conflicting action? Who thinks it's a conflicting action? Who thinks it isn't? Okay, cool, so you paid attention. Okay, of course, two reads never conflict with each other, so it's always safe to have two reads. But of course, if we write to a variable while another thread reads from it, that's a conflicting action. And we need to be careful about these conflicting actions because if we have two conflicting actions in separate threads and neither of them happens before the other, then we will have a data race. Happens before the other here doesn't refer to physical wall clock time. It's more like a logical concept which refers to synchronization. We will talk about that later. And data races, well, the standard is pretty clear about this. If you have a data race in your program, that's undefined behavior. That's not just unspecified behavior like, well, we don't know if X is going to be 1 or 42. It's really undefined behavior is bad. Undefined behavior means your execution may be broken beyond repair and very bad things may happen. For example, some of you may remember 10 years ago when there was this blackout in the northeast of the United States where the entire northeast of the United States went blackout. And that's just because someone had a race condition, data race, inside of a computer program. So beware of data races. The second concept we're going to need for this part of the talk is the concept, the notion of sequential consistency. This is even older than C++ itself. So a system has sequential consistency if the outcome of every execution is the same as if all operations would be executed in some sequential order. That is one operation after the other atomically. And the interleaving of these operations is consistent with the program order defined by the individual threads. I'll say we have one thread which has two operations A and B, and we have a second thread which has two operations C and D. Then that would give us, in this model, this would give us 6 different executions. And you can see always A happens before B, and C always happens before D. And it's very important that these operations are executed sequentially, so 2 operations at the same time is not allowed. So that's a very powerful model if you have this, and we totally want this for C++. So the question is, now consider we have this multi-core systems running and all these optimizations going on, so how could a programming language ever guarantee this model to us? And it turns out it's actually quite easy as long as these programs synchronize all access to their shared variables in a proper way. Then it's easy to get sequential consistency. So what about those kind of programs that do not synchronize their access to shared memory? Well, yeah, maybe it rings a bell. We just had it on the previous slide. Well, if they don't, then this will be a data race. So that means it's undefined behavior anyway. So here's the deal. Here's what we do. We make sure that our programs do not contain any data races. And in return, the system guarantees us sequential consistent execution. So basically, it's as if our program would run on this Lamport machine, which just executed one operation after the other atomically. It's a pretty nice guarantee to just reason about program correctness. So this concept also runs under the name Sequential Consistency for Data Arrays-Free Programs, SCDRF. And this is also the model you get, for example, if you use Java or C#. So how do we avoid data races? Well, there's the most common practice for avoiding data races, and I'm sure everyone here knows it, is by using locking. So you need some object of mutex type, and then whenever you want to work with some shared data which is protected by this mutex, you just acquire the mutex first by calling mutex lock. And as long as you hold on to the mutex, no one else will be able to lock it. And when you are done with your shared data, then you simply release the lock by calling lock unlock. Of course, in real program, you shouldn't write lock and unlock explicitly. You just use this lock guard mechanism, which I think everyone knows. And yeah, let's do some example. For example, we have two threads, and one thread is just going to produce some shared data. There's this prepared data method which just creates some data and just maybe puts it in some external data structure. And so before the thread is doing so, it just acquires the mutex by calling mutex lock. And when he's done with prepare data, he sets a Boolean flag to indicate to the other thread, okay, here's new data is ready, and then unlocks the mutex. The second thread will lock this mutex before consuming the data to avoid data races. And of course, because we don't know the order in which these two blocks happen at runtime, of course, the second thread has to check if this Boolean flag is set, and then it may consume the data. And yeah, this is perfectly fine. And if you ask people how this works, why this works, they usually tell you, yeah, because we have a mutex, and this mutex somehow makes sure that these two code blocks never run at the same time. Yeah, that's kind of a simplistic view, but it's perfectly fine if you just argue like this for this kind of program. But we are here concerned with the memory model. In particular, we saw we had all these optimizations, and yeah, so we need to just to look a little bit more into this example. And yeah, the standard identifies certain operations that may synchronize with each other at runtime. So say you have some thread which performs some operation X and then does one of these synchronizing operations A. And then we have a second thread which just has an operation B and followed by an operation Y. And at runtime, it may happen that these two operations A and B synchronize with each other. And that means that this induces some logical happens before relation on the instructions X that happened before A, that is a sequence before A, and the operation Y that is sequenced behind B. So we say X happens before Y because A synchronizes with B. And happens before here means that all these side effects that we had in X that on shared memory locations become visible to Y. So let's look at the last two slides again, now that we just know this definition. So there are two lines I intentionally skipped. I just have the slide here before. And yeah, the important the statement is here. So mutex unlock will synchronize with all subsequent mutex lock operations that are performed on the same mutex object. So this means here in this example, so if the first thread is done with preparing the data and calls unlock, and the second thread is calls lock, and of course we assume that the second thread already sees that this data ready flag has been set by the first thread, then we know that because unlock synchronizes with lock, prepare data happens before consume data. So according to this definition of data race, that's not a data race. That's perfectly fine. So once we know this, we can even see more about programs. So for example, just imagine prepare data as an operation that runs once. It never runs again. It's only executed once and then never runs again. And prepare data may be very expensive, and usually if you have a lock, you do not want to hold it for too long. So you could be tempted to just, do prepare data first, and then, you lock the mutex and only set the ready flag. And in the second thread, well, you just say, okay, I just acquire the mutex, then I check inside this critical section, I check for the data ready flag, and then I unlock immediately, and then I just see if I saw that this flag has been set and start consuming the data. And also in this example, once again, assuming that the second thread sees that data ready has been set, otherwise you won't do anything anyway, then, this unlock operation synchronizes with the locking. And once again, this makes prepare data happen before consume data. So we have proper synchronization in this example here. So of course, this assumes that prepare data is never called again, because if it would be called a second time, then of course we would have a data race. So let's see if we can optimize this example a little bit more. And here someone obviously was very clever. So the first thread just does the same thing as before. It prepares data, then it acquires the mutex and sets this data ready flag. And now the second thread, it just performs a try lock operation on this mutex. This is basically the same like a lock, but instead of blocking, if the thread cannot acquire the lock, then it will just return false. Right? Probably many people here know this. So now from a simplistic point of view, someone might be tempted to say, okay, the only reason this try lock operation here may fail is because we have a lock here, and this somehow would mean, that this, the first thread is already done with prepare data and is inside this critical section to just set this Boolean flag, right? So what do you think? Is this correct code? Who thinks this kind of code will work? You think? Yeah. How many think it will not work, this not correct code? So the other guys are unsure, but that's also good. If you are not sure about this, always assume it doesn't work, then you're on the safe side. Well, of course, but as you know, if you have a comment like this in the source code, then this almost always means that the code is broken. So, and the reason this code is broken is because we have two locking operations here. There's no lock-unlock pair, it's just two locking operations, and there's no synchronization happening between these two locking operations. So basically, this does mean prepare data does not happen before consume data, and we have a data race. So this is the reason why the simplistic view of locking is sometimes dangerous. If you just care about stuff that happens inside the critical section, that's perfectly fine. But if you just want to see program correctness for programs that do things like this, then always think in terms of synchronization, not in terms of wall clock time. So any questions about this? Okay. There's another way to just synchronize programs that do not require explicit locking, and that's using atomic variables. So an atomic variable is kind of a data race-free variable. It's your get-out-of-jail-free card in the C++ memory model. If you declare a variable atomic, for example, std atomic int, then you may read to it and write to it without any external synchronization, and that will not be a data race by itself. And another nice feature that these atomics offer is that by default, they provide inter-thread synchronization. This means if you store a value to some atomic variable and another thread reads back this value, then this means these two operations, the store will synchronize with the load. And also by default, there's a total ordering of all these, global total ordering of all these atomic memory operations, so you get this sequentially consistency. So sometimes people are a little bit confused. So when you write C++ programs in Java, you use volatile. In Java, volatile is what is atomic and what atomic is in C++. But if you write C++ programs, at least concurrent programs, do not use volatile there. It's the atomic you should use. Volatile does not provide any inter-thread synchronization. It's just something completely different in C++. And this is pretty nice, so we can just go back to this example where one thread prepares data once and then sets a Boolean flag. But instead of having a simple bool protected by mutex, we could here simply use an atomic bool. So when the first thread is done, it will set the atomic flag. And if the second thread observes that this flag has been set, if this store becomes visible to the second thread, well, that will be a synchronizing operation. So you know it's safe to consume data because prepare data happens before consume data. Always assuming that prepare data just runs once. These atomics offer more operations than plain loads and stores that may come handy in, when you do log-free programming. So just say we want to implement a singly linked list. And a singly linked list where multiple threads can call push, so push front, concurrently without explicit locking. So the way this could be implemented is by just very similar to this normal singly linked list you all know. You just have a node type, which just holds the data and stores a pointer to the next node in the list. And then you need, of course, a list head, the pointer to the first node in the list. And because we want to push concurrently, we need an atomic pointer here. So the way the push operation is implemented is also pretty similar to what we do in the single-threaded case. So first, we would allocate a new node and then just, store the data inside it. Then we will set the new node's next pointer to the current head of the list. I'm just doing an atomic load here, just to prevent data races. And the only thing that needs to be done now is just to update the head node in the list, right? So, but now there's this very complicated instruction over there, this very complicated statement. So why don't we just store the pointer of new node to this head of the list? Anyone knows why we just can't use a plain store here? Yeah?
Two people may read the head at the same time, and then you have two new heads, and you don't know which one is going to be.
Yeah, right. So there could always be a second thread running in parallel who also already set his pointer to the current head node and updated it. They update in between, and so you need to make sure that the value of the head pointer didn't change while you were just doing all the other stuff. So and there's this compare exchange methods, which is basically like a conditional store. So when you say compare exchange on an atomic variable, you say, okay, update this atomic variable head to the new value which we want to have. This is this new node pointer here, but only if the value is still what we expect, and that would be what we have set in our new node pointer here. So if this operation is successful, it will return true, and we are fine, we're done. And if someone else came in between and changed the head pointer while we were busy with other stuff, then this method will return false. So we know, okay, something has changed in between, we're not successful. So, and a nice feature this compare exchange method has is that it also tells us what is the new value, what the new value is that we have in the head pointer. So, because this expected value, it's just consumed by an L value reference and is automatically updated every time you call head compare exchange. So we can just spin around until at some point, if no one else has been pushing in between, it just starts hopefully being successful, and then, we are done. Any questions so far? Yeah? Just a few, because
So if in some other thread the value of the head has been changed, don't we lose an element if we change it afterwards because we already loaded the head before?
Sorry, somehow.
So isn't there a data race between? Isn't there a way of losing elements between head load and
head store? Yeah, this is why we don't store here. This is why we use compare exchange. Basically, when we use compare exchange, we say don't update the head node pointer if someone has changed in between.
And what do we do otherwise?
Otherwise, this compare exchange method will update automatically the next pointer of the newly allocated node. So it will stabilize. So given that at some point of time no one else is pushing anymore, this will stabilize eventually, and then you're up to date. Okay, maybe one more question. We can talk about this later, but still more stuff.
Don't you get the ABA problem here?
That's why I just showed you push and not pop. So for push, you don't have this ABA problem. It's right. Even if someone changes in between, then yeah, still the only thing you care about in push is that your list is the list structure is invariance hold, so you're always pointing to the next node and there's no nodes missing. The ABA problem isn't relevant here for the push. But of course, as you say, log-free programming is very hard, so you shouldn't, you should be very careful. You should read a computer science book about log-free programming before you do this in practice, because this push operation is very easy, but pop is not. So just a little summary of what we've seen so far. So in the first part, so most importantly, avoid data races, synchronize correctly. There's a lot more synchronizing operations defined by the standard. Usually when you just read documentation, it usually states what the synchronization operations are for these kind of tools you have. And if you do log-free programming, you can avoid things like logs, but always look it up in some good book before you do that. And what we get when we do that, when we avoid data races by default, we get sequential consistent executions, which is, pretty nice. So, but of course, we had the second part of the talk about explicit memory ordering for atomic operations. So you remember the slide of SID atomic there, where when we have talked about these guarantees you get by performing loads and stores of, on atomic objects. And there were these two little words by default, right? So what does that mean? So these guarantees, these are pretty strong guarantees. What if you somehow think you don't need these guarantees? And maybe they could be expensive on some platforms. So what about don't pay for what you don't need? Well, actually, the second thing is it's C++, right? So things have to be very complicated. And so why only have sequential consistently when we can also do a mix and match between 3.5 different models for memory operations? So, and indeed, when you are working with these atomic variables, the standard allows you to sacrifice sequential consistency just to get maybe a bit more performance out of it. But be aware that, if you sacrifice sequential consistency, basically, this could have you're losing some guarantees, and this may have some unintended consequences. So, and that's what we will be talking about for the remaining part of the talk. Let's start with the weakest model we have for atomic operations. That's basically memory order relaxed. So if you want to use it, then just whenever you do a load or store on an atomic variable, you can just say, okay, use memory order relaxed instead of sequential consistency. You just pass it a second parameter to these operations. And what kind of guarantees do we get then? Well, if you use only relaxed atomics, then you know that there's a modification order associated with each atomic variable in your program. Separate modification order, and that's just a plain concept. So there's no way to observe this modification order directly in your program, but it's somehow you think of it as a concept. And all the operations we perform in a single thread on a single atomic variable are consistent with this modification order. let's do one example. So say we have a variable x, and here in the middle we see that's my modification order. And now if we perform a store, say we store the value of 1 in the first thread on this variable, then somehow in this modification order, there has to be, the value of 1 has to show up in the modification order. We also saw that stores performed by the same thread on the same memory location have to be consistent with this memory order. That means if we, after storing 1 and then we store 2, this means somehow the 2 must show up below the 1. It cannot just cross each other. When we store data in other threads, there's no such relationship. There's no guarantee what happens if we store data from other threads. They show up anywhere in this modification order. Likewise, when we load data from an atomic variable, well, we know these loads must be consistent with previous stores we did in the same thread on the same object. So after storing the value of 2, we cannot get back an earlier value like 0 here. So these kind of guarantees you get from the standard, otherwise it wouldn't be possible to write any useful program with these kind of operations. Additionally, if you perform multiple loads in a single thread, these loads must be consistent with the modification order. That means once you've seen a particular update, you cannot later see an earlier value if you are running in the same thread, right? There's still no such guarantee for loads and stores between different threads or different variables. So when you have an execution, you can always draw up some diagram like this, where the arrows between one thread and one atomic variable don't intersect each other. But if you have multiple threads and multiple variables, the arrows may as well intersect each other. And this may have some consequences which are somehow counterintuitive. Say we have 2 threads here and 2 atomic flags. And the first thread here is just going to set both flags. We'll first set F and then G in this order, using relaxed stores. And the second thread just spins around on G and waits until somehow sees that G has been set right. So we may draw up our diagram here. We have 2 threads, and this time we have 2 different variables. And because of the stores performed by the first thread, at a certain point in this modification order, there has to be a transition from false to true. And now the second thread spins around until it eventually sees that G has been set to true. So, but what does it mean if we then load the value of F, which we know has been set before by the first thread? Well, these are 2 different variables and also 2 different threads, so there's no ordering constraint between these 2. There's no constraint between these 2 loads. We could get into the situation where the second thread actually observes that G has been set to true, and F, which we set before in the first thread, is still false. So, and if your program somehow relies on F being true whenever G is being set, then your program is broken. In particular, this means that you cannot use these kind of relaxed loads and stores to synchronize the data access for non-atomic variables, like we did in this producer-consumer example. If you would do it using relaxed load and stores, this would be fundamentally broken. But still, there are some applications where, maybe you can get away with relaxed atomics. So say we want to increment a counter. And the way we might do it is just, we have this counter variable x here, and so we first load its value, and say we get back a value of 0. And then we try to increment it atomically using these kind of compare exchange methods you just saw before in the log3 queue example. And we say, okay, update this counter to 1, given that the current value is still 0. Of course, it could be that some other threads runs concurrently and also writes to this memory location, so we cannot use a plain store. We have to use this compare exchange method. So the way to just model these kind of operations in these kind of diagrams is just, basically this is like a store operation. So first we have an arrow going from the thread to the modification order. And if it's not then it will see some value. And if it's not successful, then it will return the current value, which is just, in this case, going to tell you, okay, I couldn't update it from 0 to 1 because it's already been 1 before. So, and then you try again and until it eventually turns into a store. There's still no constraints how these operations are ordered with respect to other memory locations or other operations performed by other threads. So when we can actually use it, consider we have a worker thread. We have some worker threads, and each worker thread performs, say, 100 different tasks. And after each task, it just updates this progress counter C. So and instead of using this complicated compare exchange loop we saw before, you use the shorthand notation, which is fetch add. You should always prefer fetch add over this compare exchange loop, just because it's simpler, and on some architectures you also get more efficient assembly instructions for this. But let's not talk about performance yet. So and the main thread just kicks off n worker threads and waits until they are completed, so just joins them. And then the thing we can know for sure is that after all these threads are completed and terminated, then the value of the counter will be 100 times n. The reason we know this is, first, joining threads synchronizes with thread termination. So after we joined all the threads, this means all increments that happened in the worker threads happened before our assert in the last line of this example here. And the second thing that's even more important here is that we do not care about the specific order in which these increments happen here. So we don't care how they are ordered with respect to our main thread. In the end, we just care that every thread has called increment at 100 times. So this perfectly works. Now, to make this example a little bit more interesting, let's just add another thread which just does a progress bar in your application. So this thread will relentlessly read the value of the counter and update the progress bar. And of course, if you have a progress bar, you do not want that this progress bar runs backwards in time. So I put a little assert here which just says, okay, whenever we read a value, this value should be at least there should be at least as much progress in your worker threads as we saw before. Does this assert hold? Well, actually it does, surprisingly. The reason is because reads performed by a single thread on a single object, and that's exactly what we have here if we just only read the progress. They must be consistent with the modification order. That means once we've seen a particular update happening, we cannot see an earlier value if we read back later. So this is perfectly fine. Now, as to the question if we have progress, so you certainly want your progress bar to be moving forward, the more progress you have. Well, the standard says that side effects in one thread have to become visible to other threads after a finite amount of time. So whatever that means. Well, it works pretty well in practice if you do stuff like progress bar, but you shouldn't rely too much on it if you write mission critical code. So if you need a time guarantee, don't do it. For progress bar, it's perfectly fine. So we get a perfectly forward moving progress bar here. And that's enough for the relax model. Just want to show you acquire release now. Oh, we have some time left. Acquire release gives you all the guarantees of the relax model, and in addition to this, it also provides inter-thread synchronization. So this means whenever you store a value using a store release, you do store release, then and another thread just observes this value using a load acquire operation, then this means that the store synchronizes with the load, which, as you remember, means that all operations that we did before the store release in the releasing thread happen before the operations we do after the load acquire in the acquiring thread. Basically, it's the same as we saw before, this producer-consumer pattern, where you just produce some non-atomic data, and then you store some flag, say it's 1 here. And if the other thread eventually reads or observes that the flag X has been set, then we know we can safely access this produced data, and because basically the store to this non-atomic variable happens before the assert. Of course, there is something that's very important here is that the synchronizes with relation. It's a relation that refers to a particular execution at runtime. So just having a load and store in your source code doesn't give you any guarantee. Actually, you have to make sure that you see the value that has been stored. If you don't see it, then you don't get any synchronization at all. For example, if you just do a store release in one thread after preparing some non-atomic data, and the second thread just loads this value, you don't get any synchronization unless you observe actually that X has been stored in the first thread. So in this example, if you just load back the initial value of X, that's no synchronization here because the load doesn't see the value that has been stored, and that's database. Another nice property in this acquire-release model is, well, actually you get some kind of transitivity. So say we do the same game with 3 threads instead of 2. So the first thread just produces some data and sets this atomic flag F. And the second flag spins around until he actually sees, okay, F has been set by the first thread. And instead of consuming the data we just stored in N, the second thread just sets another flag, say G. Well, we know by this acquire-release model that setting the flag G, or storing the data in the int, happens before setting the flag G. And if then a third thread just observes that G has been set, this means by transitivity that basically storing the data in N happened before we run our assert. So that makes acquire-release, transitive model. Okay, we just have 15 minutes left, and I want to leave some time for questions, so I will skip over this consume model. Maybe you can watch it in the recordings later. The only important thing you should know about this consume model is that it breaks these nice transitivity in the happens before relation, and you get real weird effects even if you just consider stuff that happens in the same thread. And it's so weird that actually compilers today cannot handle it correctly. So most compilers just say, okay, let's do acquire-release instead. And personally, if I have some mechanism that even the compiler doesn't understand today, I don't want to use it as well, because then I think I don't understand it. There are people who tell me otherwise, but okay, if you understand it, use it. I think I understand the guarantees, but I still feel uneasy about using it in practice. In particular, if your compiler doesn't support it well, then why should you use it at all? So I will go to now focus on a more important question. We saw that we had this acquire-release model. We had all these nice guarantees. We had inter-thread synchronization. We had transitivity. So why would anyone in the world use sequential consistency? Isn't acquire-release already enough for everything, every problem you practically have in your life? So already also be a question that I've been asking myself when I read about all this stuff. So why can't we just simply use acquire-release? Isn't that enough for everything? Well, let's look at the example from we had on one of the first slides again, this Dekker algorithm. You know, you have a critical section, and you have 2 threads, and every thread has a separate flag. And whenever one thread just is going to enter the critical section, just sets its flag and tells all the other guys, hey, I'm going to go inside this critical section now. And if you don't see any other flag set, then you think, okay, I'm safe to just enter the critical section, right? It's a very simple algorithm. Even if you don't use it inside your program, feels like a good model should support algorithms like this. Well, there's something that's fundamentally different to all the other examples about acquire-release that we saw before. So usually the pattern was we observe some value that has been stored inside this inside some atomic variable, and we do something based on the fact that we just observed that something has been stored. Now in Dekker's algorithm, well, we do the opposite. We just do something if we didn't observe that the flag has been set here. And so there's no particular synchronization that's going on here. In particular, what could happen is that, yeah, you have two threads running concurrently and both want to enter the critical section and both set their flag. So the modification order will look like this. And then you read the other thread's flag. And yeah, and because we don't have sequential consistency, we don't have any total ordering of these variables, yeah, it may well happen that both threads see that, do not yet see that the other flag has been set. So what happens here basically is that both threads may run into these critical sections without any synchronization, and then terrible things will happen. So let's do it again in the model of sequential consistency. What do we know? So if you want to use sequential consistent atomics, we can say, okay, do you loads and stores and pass this memory order sequential consistency into this, to the operations, but it's the default, so you don't have to. You can just say load and store, and then you will get sequential consistency. And what happens in the sequential consistent model is that you have a total order of all memory operations, and you have this interleaving. This means if you draw up these diagrams, you can as well draw all these arrows horizontally. So there's always a total order, and all the threads agree about this order. So another way to put this is that at any given time in your program, every memory location only has one value. Stuff like we had before where just, yeah, for one thread it has been true, and the other thread says, okay, it's false. It doesn't happen in the sequential consistent model, at least if you don't have any data races in your program, right? So if you use sequential consistency, Dekker's algorithm will work fine. Of course, you shouldn't use it. You should, of course, always use mutexes provided by the standard library, but it's just a very simple example with two threads and two variables, and if this fails in the acquire-release model, that means you should probably be very careful about acquire-release. So when would you use non-sequential consistent atomics at all? Well, I already told you, okay, one reason to use them, maybe you want some more performance. And in particular, on some platforms like PowerPC, sequential consistency can cost much more than using these more relaxed operations. We also saw there's some use cases that work pretty well if you do only relaxed operations. For example, these kind of operations counters we had for these progress bars. And there's stuff that works well if you use acquire-release, like, for example, reference counters or, yeah, say, double-check locking patterns for lazy initialization. But if you need these, you could also use shared pointer or std call once. If you need something like this, the library brings you features you want. And the most important thing is that before you use these kind of operations, you shouldn't do it too liberally. You should always profile your program. You should see, yeah, where the real performance bottleneck is. Because often it's not the atomic operations, often it's somewhere else you don't expect it to be. So what have we learned in this talk? First, most important thing, beware of data races, synchronize properly. Second thing is, well, actually, that with C++11, you do not need to care about system-specific optimizations. You just can rely on these guarantees the memory model gives you, at least if you have a bug-free compiler, and reason about your algorithms. And the last thing is that, yeah, if you think sequential consistency is too slow or you just profiled it, then, yeah, you can use more relaxed operations. Just sacrifice sequential consistency, sacrifice a bit of causality in your program to get more performance. And some of you may have noticed before, we're also hiring C++ developers. So if you're just looking for a new job, then maybe just come by to our lunch and have a little chat with us. So okay, that's all. Questions?
I have two questions. So the first is about ARM. As far as I know, some
Can you just speak up a little?
Okay, it sounds better now. My first question is about ARM. As far as I know, ARM memory model, maybe not the ARM memory model, but some ARM CPUs do not provide total store order for writes to the same memory location. So does it complicate somehow the life of compiler developers? How do they provide this total order for writes to the same memory location when the architecture doesn't provide it, or when certain CPUs don't provide it? The second question.
Well, so you're referring, for example, to the ARM architecture. Well, usually the compilers, the first thing is that the compiler has to make sure that you get these guarantees by using whatever means it needs to be done. For example, using very complicated assembly instructions. The second thing is that, of course, on these new ARM architectures, you have more guarantees by the hardware. So if your compiler just compiles code for a specific architecture, it can always create better assembly code that needs less overhead. I'm not sure if that answers your...
Okay, maybe no, maybe you can take it offline. I have another question. C++11 memory model allows out-of-thin-air values when you use relaxed atomics. And out-of-thin-air values are not allowed by hardware memory models. So do you find it a little bit strange?
What kind of memory model? Sorry, say again.
In C++ memory model, if you, for example, have readx and then you set value of y to the value of x that you have read, and the other thread does a symmetric thing, and this is done using relaxed atomics, then both threads, for example, can read value of 42, one from x, one from y. So this is what is called out-of-thin-air value. You probably know.
Yeah, the out-of-thin-air problem is it's a very tricky problem. So the setup is like this. You have one thread that reads x and simply stores the value to another atomic y. The other thread has first reads y and simply stores the value it read to x. And if you just use the memory, if you just look into the standard, what the memory model says about that, if you just, it's an axiomatic model, it's not an operational model. You don't have operational semantics with relaxed atomic. That's a big problem here. It's a theoretical problem. And so it may happen, and you can draw up these diagrams, that actually somehow you get a circle in this diagram, right? So you have some infinite dependency circle, and then the value may be, say, 42 or whatever. And the standard just, says, okay, we don't know how to define this away, but we just say implementations should assure that these cycles do not happen. And on real hardware, there's no, on current hardware, there's basically no way to make this happen. But
is it planned to be fixed?
What?
Is it planned to be fixed?
Well, there's some scientific papers about redefining the memory model. So you basically get these kind of guarantees I told you here, but just use some other formalization that is a little bit more operational and that prevents the execution of out-of-thin-air values. And I'm not entirely sure, but at least as far as I know, they solved the problem if you do not have memory order consume in your program. But there's a paper, I can show it to you. I have it somewhere on my machine. Okay.
Hey, great talk. One practical question. It's quite likely that we can improve the performance of our multi-threaded algorithms with the atomics because we don't need a explicit synchronization point. But there are memory reads and writes, so that means we need still cache synchronization. Is there any research about how this affects the performance of non-blocking algorithms?
So you say you have an architecture where you have a cache coherency mechanism that is basically very slow, or what are you?
Yeah. As far as I know, is that multi-core processors have only shared level 3 cache. So we need to write back level 1 and level 2 cache.
Yeah, that's
to
basically the reason.
3 back.
The real reason why we have executions like this. It's basically because if you set a store value in one core, then the cache coherency ensures that eventually all the other cores will be able to see it, but it's not immediately. If you just do move operations in memory on x86, well, you may get into this this kind of scenario. So the standard already has this acquire release semantics, which just reflects these kind of operations on real hardware. If you use acquire release and your hardware just gives you this guarantee, then your compiler can use plain loads and stores. So, and if you need sequential consistency, then basically you need some operations which ensure that the memory access is locked somehow. For example, on x86 by using a lock prefix on your instructions.
So which means that it affects performance then, in some way.
I fear these kind of questions, so let's see what he...
I mean, it's anyway hard to measure, but is there any research about that?
The thing is why talking about performance here would be another 1 hour talk, because the thing here is that there's so many levels. And you cannot quite make a statement. If anyone makes a statement like, okay, acquire release is twice as fast as sequential consistency, that's a lie. Because you cannot tell this in general. There are 2 things that are going on here. One is compiler optimization. And in particular, if you use sequential consistent atomics or acquire release, then the compiler has to make sure that it somehow stores all the temporary copies of your global variables back to memory. So that's the compiler optimizations here going on. And that how much you can optimize a way just depends on your program. The second thing is that, for example, on x86, if you need sequential consistent stores, you need to use these operations which have either an explicit or an implicit lock prefix, like exchange, for example. And these usually in older processors, these instructions would just block the entire bus and it get you terrible performance. But currently, modern processors, they lock based on cache lines. So actually, so how much you lose by applying these kind of operations depends very much on what the other cores are currently busy with and what they are doing. Even Intel in their manual, they don't tell you how much these kind of operations cost, so you can only benchmark it. And if you do, sometimes you do not see any difference at all if you just switch from sequential consistency to memory order acquire. That's why I just say benchmark first, and then see where your problem is. And if you just meddle with this, then you should probably benchmark a second time.
More questions, please.
Hi, my question is kind of similar, but not about atomics. So if you have a weak cache synchronization protocol, and you use non-atomics, and the standard says if you have different memory locations, you can access them fine with reads and writes from different threads. But now I think that if you have like 2 cores and they have the same cache line, and it's just a normal variable. These are normal variable accesses to different variables in the same cache line, and not using atomics. So how would this?
Well, the first thing is, I understand. The first thing is that the standard says it has to work, whatever means it takes. The second thing is that with architectures where you need to take care about adjacent memory locations, this means it has to generate some code that it is either expensive or it has to just pad all your variables. Huh?
Was the question about non-atomics or about atomics? Non-atomics.
Yeah, but even with non-atomics, it's like you update a single byte. You mustn't. So usually in a single-threaded model, for example, it even may happen for older compilers if you write concurrent programs and you don't have a data race in your program, not in these terms of the standard, and you just update a single byte, single memory location, and the compiler may generate actually read. You just may read all 32 bits from memory and then write back all 32 bits to memory, even if you update a single byte, and that's not allowed in standard. And the same thing is if the architecture can guarantee you that you actually can update single memory locations using CPU instructions, well, that's a bad thing if you use this memory model. This means that the compiler somehow has to pad all the variables or do whatever it takes. But basically, yeah. You have a comment on this or another question?
Well, this came up just yesterday on Thursday on the reflector again. And this was discussed heavily. And the point is that all architectures today actually have single byte stores. And it only affects the stores, because for the read, you can always just throw away what you don't want to read. But for the stores, all architectures actually have single byte stores. So if you have a change of your memory location and you only change 8 bits or 16 bits of that, the compiler has to use that instruction that only writes 8 or 16 bit. And GCC changed that in 4.7, and all modern compilers do that correctly now. Old compilers do that not correctly. This was one thing, and another point I wanted to make is, well, you said correctly, before you actually optimize, you should profile. But then you also said, well, profiling is very difficult. And I think that is very true. A lot of developers don't have NUMA machines under their desk.
In particular, the outcome may depend on the architecture you're running it on.
Exactly. So sometimes you actually have to think in advance, well, okay, where is this actually used? And is that used in a context where I may get a lot of false sharing or not, and all these kind of things. And, well, just saying profile first is probably not the correct thing. I think you actually said correctly. Before you actually want to use anything else that sequentially consistent, think. And think twice, think 3 times, and then ask another expert, and then you might actually optimize.
I second that. So the way you just should take this profile first is just make sure that your program is not somewhere entirely else. If you're just in the setting now that you already have performance problems. So, and we also sometimes have performance problems, terrible performance problems in our software, but so far they are usually not related to these kind of operations. So just
Maybe tell them about the problem.
I know what you do. So okay, that's a nice thing. So these are the recommended instructions a compiler should use on x86 for atomic operations. If you still use Visual Studio 12, well, Visual Studio 12 does a terrible thing, because what we have here, we just do the synchronization, the log prefix, when we store a value. So if you just store a value and then you read it very often, you don't have any big performance problems with this. The way these atomic operations are implemented in Visual Studio 12 is that they actually do the logging when you read variable. And that's a terrible thing, because we had some atomic flag in our program, and before we had C++11, we used this volatile, which doesn't give you any portable guarantees, but on Visual Studio, Microsoft says, okay, it's performed atomically, and so we said you just had a volatile in there, and then we switched to STIT atomics, and suddenly our software was terribly slow. And this was all because we had multiple reads on this single variable and the single flags in many, many locations. And Visual Studio would always generate this kind of assembly where you actually had the log prefix on the read operation. So it did use a logged OR with 0 for an atomic read, sequentially consistent atomic reads. And it was terribly slow. So as long as we use Visual Studio 12, we just switch back to the evil volatile, which you in general shouldn't do. But now with Visual Studio 13, they did it the right way. They generate the recommended assembly, and it's okay. Yeah, thanks. Okay, that's horrible versioning. So Visual Studio 2013 is Visual Studio 12, and Visual Studio 2012 is Visual Studio 11. So I don't know who came up with these kind of version numbers. So, okay, thank you.
Okay, the time is more than over. Thank you, Valentin.